now we start recording. What a difference 2 days makes. My watch says it's about 30 degrees cooler right now than it was on Tuesday. Thank goodness. This is much better. I can work with this. So we have, just to keep reminders in terms of what's coming up, the next thing that you should be working on right now is homework 1, if you haven't finished it already. Make sure that you do the final step of entering your 8-digit ID to actually submit. Just hitting submit once isn't enough. I have that layer built in to keep people from submitting accidentally. So you do have to enter your ID number to really submit for real. By the way, if you ever accidentally submit before you wanted to, or you want to go back and change an answer before a due date, that's totally fine with me. Just send me an email and I can reset the database so that you can change your answers back again, so long as it's before the due date, obviously. I haven't put it up yet, but then after that you have a third formative assessment, and then there will be another homework. So, and just as a reminder, the week of, let's see, it'd be the 12th, 13th of October, I'm going to be out of town at a conference, so we won't have class or office hours on that Friday. So that's been on the syllabus the whole time. So not too much going on, just the usual stuff. Any questions on schedule, logistics, stuff like that? Cool. All right, then I'm going to shut this down. So what were we talking about last time? I have a picture up. Let me share the screen zoomer so you can see what I'm looking at here. There we go. What were we talking about last time? What do you remember from Tuesday?
Random effects for time.
Yeah, random slopes for time is the new thing. And when would you potentially need to have a random slope? Go ahead.
If you expect people to have different changes over different rates of change.
Exactly, different rates of change, individual differences in the aspects of the trajectory that describe change over time. So I'm saying it that way, individual differences in aspects of the trajectory, because for complex trajectories, it's probably going to take multiple fixed effects to describe it. And as long as you have enough occasions, you can have random slopes in every part of that. So all we've had thus far is a random intercept. We're transitioning into the idea of adding random slopes, which what they do sort of conceptually and from like a researcher's point of view is answer the question, are there individual differences in change over time? From a statistical perspective, what they do is allow us another intermediate alternative between compound symmetry, everything's the same over time, versus unstructured, everything gets to be what it wants. Random slopes hopefully do as good a job as unstructured, but while requiring fewer parameters and not requiring balanced data and not requiring equal interval data. So they're a very flexible way to model differences in variance and covariance over time, as we will get into some of the details today. Yeah, that was the big thing. We did a little bit of new notation. So I have, for instance, let's see. Yes, actually, let me do a segue into what I wanted to say. What model would be consistent with this top left picture here? What model would predict these types of trajectories?
Univariate repeated measure?
Yeah, univariate repeated measure, so random intercept in the model for the variance, but what in the model for the means? With respect to time?
Just the grand mean?
Yeah, just a fixed intercept, an empty model. So if we start from an empty means model with only a random intercept, and by the way, only differentiates models with extra random effects, there is always an E. So there's always a residual variance. That's always in a model. So it's a question of what else do we need. So if we were to use our new multi-level notation to describe that empty means random intercept model, we started looking at this, a new way of writing the equation down. So the idea of the multi-level structure is to take all of the components that would eventually differ across persons and represent each component as its own separate level 2 equation. So beta in this notation system is not a parameter anymore, it is a placeholder. It holds fixed and random effects. So the way that each person gets their own intercept is a combination of the fixed intercept, which we're using gamma for in red, the random intercept deviation for each person, and you put them back together again, and that's how we get each person's intercept. And in a model that doesn't have time in it, the intercept is the mean over time. Once we add time into the model, which we started doing, this is slide 12, then the intercept becomes the expected outcome given by the model at wherever time 0 is. So in most of the examples I'll show you, it's at the beginning, but it doesn't have to be. Just somewhere within the scale of the data would be ideal. So this model on slide 12 does not yet have a random slope in it. It only has a fixed slope, which means what it says is that everybody changes the same. And we started talking about effect size for these things and what happens with variances, and we will see that as well. Okay. I think we left off talking about, yes, the idea of random intercept variance. So the big picture behind this slide that we went over last time, anytime that you explain level 1 residual variance, random intercept variance at level 2 has to go up. Has to. The extent to which you will see that depends on the size of the reduction in the random or the residual variance at level 1, as well as the number of occasions. So the correction factor that gets subtracted, here it is, here's the subtraction version, from the observed person mean variance or person intercept variance, depends on the number of occasions as well as the size of the residual variance. So as residual variance goes down, less gets subtracted off, and then the result is a higher value for the random intercept variance. So when you see that happen, do not panic. It is a consequence of how the model estimation process works. Okay, I think those were the high points. Anything that you want me to go back over or have questions about based on what we covered on Tuesday? Or otherwise? No, we're good? Ready to keep rolling? Shall we? All right. So more on the idea of what only having a random intercept implies. So regardless of what's happening on the mean side of the model, we're focusing on the model for the variance for the next couple slides here. Random intercept models imply that with respect to person dependency, with respect to individual differences, there's only one kind. People differ in their intercepts, and that's it. So that implies parallel change over time. It doesn't matter where the intercept is in terms of where time 0 is because the lines are parallel, and the differences between people would be expected to be the same at all the occasions. So the way that we're specifying our random intercept when we use both G and R, we have a G matrix, as it's called, which is our level 2 random effect variances and covariances. So the term effect is a superordinate term. Intercept and slope are two different kinds of effects, but you can just say effects as a general term. Then we have level 1 R, and in this picture, it's type equals VC, or an independent or diagonal structure. And that's a testable assumption, but that's what this type of model would imply unless you add something to it that would then allow a different pattern of covariance. So in our parlance and in stat terms, we would say that this R matrix is conditional. It's only the within person level 1 residual variances and covariances that show up in R. When you put the contents of the G matrix back together again with the R matrix, then V, the result, is the marginal prediction, or what I call total, or put back together again. So the overall pattern that is implied by you only have a random intercept is our friend compound symmetry, equal variance, equal covariance. So equal slopes then, another way of saying the same thing. If we have a model that has a fixed effective time, a fixed slope for time specifically, but we don't have a random effect, then this is the type of pattern that it's predicting. Everybody shares the same linear slope for the effective time. And that'll be true in nonlinear change models too. The idea is that if it's fixed only, it's the same for everybody. It's an estimated constant that describes the rate of change. For those of you who are interested in the derivation as to why these things work out the way they do, this is in Chapter 5. If you wanted to use the model equation to figure out how the model predicts the variance at any occasion, It would go like this. The variance at a particular occasion is a function of the model. So just this part right here going in. The variance of a constant is always 0, so they fall out. So we're left with just the variance of the U0 random intercepts. The variance of a constant falls out again for time, and the variance of the e's. So that boils down to those two terms. Likewise, when you factor out all the constants with respect to which occasion is which, the predicted covariance between any two occasions is just the random intercept variance. That will change once we add a random slope. So I'm trying to drive home this point as a point of comparison. When you only have a random intercept, this is what you're saying, constant dependency. In terms of matrix equations, so you will see this written out like this in a lot of sources. So I want you to have seen it and not be afraid of it. We are summarizing all of the data for each person in the matrix equations that are on this slide. Each person gets their own set of matrices, and they all end up getting stacked together. So I have Y, which is going to hold all of the occasions for one person. So that's 4 occasions in this example. I have X, which is called a design matrix in other contexts, but the job of X is to hold the predictors that are to be given fixed effects, fixed intercepts, or fixed slopes. So the first column here, why do I have a column of 1s in this? What's that for?
Intercept.
That's my intercept. So the column of 1s would multiply gamma 0, 0, the fixed intercept coefficient to be estimated by the model. And this second column would be time if I centered it such that the first occasion is 0 and this person had equidistant occasions. Doesn't have to be that way. These numbers could be whichever occasions a person contributes. So we have the predictors that are going to be given the fixed effects in X. The gamma here is the matrix that contains the fixed intercepts and slopes to be estimated. Then we get to our friend Z. Z is a matrix that holds the predictors to be given random effects. So because not everything that has a fixed effect has a random effect and vice versa, they're in 2 different places. So this is the little column of 1s that you've seen in some of the slides that wraps around the G matrix to create the right shape to be added back to R to become the V matrix. And each person has a random intercept then that would multiply their values. So this is a constant addition to a person's score. Another way to think about this is that Z is a column of factor loadings because random effects are latent factors. So Z is lambda in an hour and a half from now. E then are my residuals, 1 for each occasion. So if you do the multiplication, it works out to be just the model as you're typically used to seeing it. So this equation describes how we come up with the predicted value for each person for each occasion. How we get the predicted variance and covariance then is this version that you've seen a couple times, but now hopefully will make a little bit more sense since you know what Z is. So how we build V is for each person. Each person has their very own V matrix based on which occasions they have and when they were measured. At this point, the only thing that's in Z is a column of 1s because the only type of individual difference we have is a random intercept variance in G. But when you add it back to R, you get our friend V here. So this is a point of comparison again. All right, so intermediate summary. We have now 3 different choices that we've seen with respect to what the model for the means would look like for time. If I say it's an empty means model, that means there is no time in the model. You have one fixed intercept and it assumes there is no change. In some situations, that's actually what you may end up with. So if you're in a fluctuation context, if you're measuring something observationally that just happens without you and you're not trying to fix it or improve it, you might not need an effect for time. Saturated means is the ANOVA model. As many fixed effects as there are occasions, that only works in balanced data. The same caveat about what the means would be if you have missing data. The means that come back from a saturated means model will not match what's in your actual data set. Like if you run descriptives, you won't come up with the same means. These are the means that are being estimated under an assumption of missing at random, which means conditional. So it's the means that you should have had you had complete data. There's a whole lot of subjunctive tense in there, and I'm being sort of deliberate because we never know if it's right. That's one of the tricky things about the assumption of missing at random. It's not testable. By definition, you are missing the information you would need to test it, so you just got to believe. And shout out to, in both classes this week, one of the readings is Craig Ender's Missing Data book, chapters 3 through 5. He does an infinitely better job of describing not only how maximum likelihood works, but also what MAR means in this context. So if you haven't read those chapters, I would really encourage you to do so. His writing is very clear, and it's very helpful, I think, to understand sort of from a computational perspective, like how this all works together. Fixed linear time is the one that we've added this week. Just the idea that we have a fixed slope that multiplies time. So this isn't any different than any other slope you would have learned about in regression class. It's the change in y for a 1 unit change in x. X is time. What a unit is completely contextual on your study. So when you're writing up a results section, you would never want to write 1 unit in time. 1 week, 1 day, 1 year, 1 month. It's up to you what a unit is, but it should be meaningful in the context of whatever you're studying. The advantage of using a fixed slope to try and describe a trajectory is that you don't have to have balanced time. You can draw a line through whatever points somebody has and make it work. As I noted, it will, anytime that you explain level 1 residual variance, such as by adding fixed time, the random intercept variance will have to go up as a consequence of that. And up to this point, all we've done is add a random intercept variance to our G matrix, which predicts constant total variance and covariance over time. Okay, before adding random slopes, I thought it might be good to start the example. Is that okay with everybody? Because that will be what homework 2 is about in a couple of weeks. Homework 2 is one of the easier ones because the entire purpose of homework 2 is to get you used to looking at output for longitudinal models. So there'll be questions like, what's the random intercept variance? And your job is to scroll and find, which sometimes is trickier than others, particularly if you're trying to teach from 3 different software programs that each put the random intercept variance in a different place. So to get you used to that process of going through output and finding the things that you care about, I have an example. So example 5 is what I have here. This was posted, I think, for Tuesday. I have a note, though. I'm not planning on going through all of this in class. The second half of it is designed for the folks who are simultaneously taking SEM or who have already taken it. And unless I have a bunch of extra time in class that I hadn't planned on, I'll probably just record videos from my basement for that part. That way the folks who are interested can watch it and other folks don't have to. But I'm trying to make the connections because everything that I'm talking about in this class can be estimated equivalently as a structural equation model. I'm using multi-level models because I think it's easier pedagogically to understand them because they're closer to regression and it's easier to estimate. But it is still, you could do all of this with SEM. So I want to make sure folks understand those connections. So, anywho, the data for this example are fake, of course. I have an outcome. You can pretend it's whatever you'd like, but that's literally the name of the column. It's just called outcome. And I have 2 versions of time in the data set. I have wave, which is 1, 2, 3, 4, because these are 4 occasions of data. And I am going to subtract 1 from wave to create time, which is going to be the predictor that goes into the model. So in the specification of the syntax, both time and wave will go in there because they have different functions. And this sample has only 25 people in it. So one of the other things that I'm trying to demonstrate is how your answers might change if you use maximum likelihood versus residual maximum likelihood, which is another difference in terms of estimation. SEM does not have residual maximum likelihood. So I'm just loading in the data, centering time. It's already been stacked, so I didn't have to do that. So most of the code you've seen looks the same. The only exception is that I wanted to create a version of wave that had the last occasion as the reference in order to fit a saturated means model, and so I had to make that new variable in R in order for it to do that. And I have a caveat here that no one has responded to yet in the year and a half that this caveat has been on the internet, of me describing how I'm working with the different packages and their limitations. And if I have this overly complicated or incorrect, someone please correct me. But this is the best that I could do on my own. And after asking all the people that I thought should know better. I did not get any further. So first thing then, this is page 2. I'm estimating the answer key. The first thing I'm doing is, because I have only 4 occasions and because they're balanced, I can fit a saturated means model that will perfectly describe the mean for each occasion, and I can fit an unstructured R-only model for the variance that perfectly describes the variances and covariances. The reason I'm doing this is to try to get a sense of what my eventual predictive model should look like. In the SEM class, the combination of saturated means and unstructured variance is the H1 saturated model. It's the same idea. It's the best possible model that we will compare against to see if our model is close enough to the best. So this you've seen before, but I have wave being treated as a factor variable, as a categorical variable in the Sas syntax, so it's on the class statement. That means Sas understands that what I want is one of the occasions to be the reference, and then I need n-1 dummy codes to get me slopes to contrast the reference with each other occasion. I've added ls means in Sas to print out the actual means and to give me all the mean differences. The R matrix, I don't have a random intercept yet. This is just unstructured R, so everything gets to be what it wants, all in one matrix. In Stata, unstructured R shows up right here in the residuals line. IB last puts the reference group for wave the last occasion to match the Sas output. I'm asking for the R matrix and the correlation version to be printed as well. And then an F-test for mean differences across waves that is not provided by default in Stata, as well as the means at each occasion and the pairwise mean differences. In R, we're back to GLS. So the model statement looks like this. Outcome is a fixed intercept plus wave 4 as a factor variable, again, so that the last occasion is the reference. The correlation option, with all this stuff behind it, gives me the unstructured correlations, and then the weights option gives me heterogeneous variances. So given the correlations and the variances, I can figure out what the covariances should have been, and vice versa. So I'm asking it then to print the model output, to print the -2 log likelihood, and to print the total variance, which it doesn't do by default, which is weird. I'm then asking it to print the R and R core matrices for the first person, as well as the means and mean differences, and an F-test for the mean differences across time. So you've seen this before, that's why I'm going through it a little bit more quickly, but are there any syntax questions? Okay, so here's what we got. I got my text boxes moving around randomly, because, you know, why not? Whatevs, the words are still here. So Sas output is what I'm looking at here, but it looks pretty much the same in the rest of the packages. Let me see, what do I have? Yeah, so you can follow along if you want to. The text boxes are going to kill me, though. No, I don't want Zoom. What I want is my PDF copy so that I don't have to try to figure out where all my little notations went. That's what I want. There. Here we go. That's what it should look like. Good enough. So, covariance parameters 10, because I've got 4 occasions and this is unstructured. So I have 4 variances. Here they are. I have how many covariances? Softball question. 6, yes. So the matrix is symmetric. So 2, 1 is the covariance between occasions 1 and 2, and that's the same number there. So you only need to look at the top or the bottom parts of that. What do we think about these variances? Same or different?
Different.
Different in a pattern or different kind of random?
Pattern.
Pattern, yeah, they're increasing over time. People are spreading out. Like that's a clear signal that some kind of individual differences and change is happening here. Covariances are necessarily going to be different over time if the variances are different, because variance is part of the covariance calculation, but we can look at the correlations to get a sense of just the relationships that are scale-free. And it does look like occasions that are closer together are more related to some extent. So not constant would be what I would call this. Here are all of those individual parameters that made the R matrix. So it lists them all out. And the notation here, UN1, 1, that means in the unstructured R matrix, this is row 1, column 1. So any entry in this table where the same number is in both spots in the parentheses, that's a variance. It's on the diagonal. Any entry that does not have the same number in both spots is a covariance or a correlation of some kind. This likelihood ratio test right here is not terribly useful. It gets printed by default. What it's testing is whether we need anything besides E. Basically, is there any dependence at all? Yes, there is. So not terribly helpful because it's not very specific. Here are the fixed effects of the model. So wave 4 is estimated at 15. And each of these is a slope that differentiates that wave relative to wave 4. So it looks like the earlier occasions are lower, significantly so. If I were to take these 3 slopes and lump them together into a joint test as to whether there are any differences across the 4 occasions, that is what the F-test here is telling me. So in ANOVA parlance, that would be your omnibus mean effective time. An F-test more generally is used to lump together multiple fixed slopes. Because fixed slopes can be positive or negative, F is in a squared metric. And F is per slope, so that like the reference point for like what would be random is just an F of 1. If I take my F-test statistic, which is 23 here, and I multiply it by 3, what would it become? A little bit of stats trivia for you. Anyone? Greek letter?
What about the Wilson?
The question was, if I took my F here and I multiplied it by the number of slopes that I added together to make my F, what would that become? Chi-square, yes, zoomers. Zoomers for the win. Now, why am I mentioning that? Because you might get a chi-square in your output instead of an F. It's telling you the same thing on a different scale. F is per slope, chi-square is not. The difference in terms of their reference distributions that would create the p-value is denominator degrees of freedom. Chi-square doesn't have any, F does. So then we have the means at each occasion that are put back together again with the fixed effects. So out here in red, I have listed how these were created as linear combinations of each intercept plus the slope that differentiates that occasion from the intercept. And it looks like, yeah, the means are increasing over time. Significant mean differences pairwise, if you care about such a thing. And so I made some pictures. So this plot on the left is the data. Since I only have 25 people, it's easy to make a plot. In data sets where you have a lot of people, you might want to take a random subset to make your plot with so that the lines don't just become a solid blob. But then I have the means per wave from the saturated means model in here in red. And the bottom picture is variance per wave in blue. So these are the trends that we're going to try to fit. So the red line looks fairly linear. Not a coincidence. That's how I simulated the data. Blue line. Does that look linear to you?
No.
Not really. Looks like there's a big difference between 3 and 4 here. Yeah, also not a coincidence. Turns out that that is what a random linear slope model implies. I'll show you the math in a little bit, but the short answer is it implies quadratically increasing variance. It's a parabola prediction. So what we're looking at is the right side of the parabola. So this model, saturated means where each occasion gets a different mean via the fixed effects, unstructured variance where we have all separate covariances and variances estimated, is only possible if you have balanced data, and it's only possible if you have few enough occasions to where you could estimate everything at the same time. If you have unbalanced data, or you have too many occasions and this blows up, here's an alternative. So this is still saturated means, but it's only a random intercept. So if you have unbalanced data, just for the purposes of making a picture, you can temporarily round your occasions into intervals so that you can fit saturated means to just get a sense of the trajectory. Don't ever use the rounded version after that, but just to make a picture with. The unstructured variance model has been replaced with the random intercept. That this will always be estimable so long as you have at least two occasions. They don't have to be balanced, they don't have to be complete. So that part is really not that informative. The purpose of this would just be to get the trajectory implied by the saturated means. So then the difference in the code is in the variance model. So we're using a G matrix to hold the level 2 random intercept variance. We're using a diagonal R matrix, just the E variances on the diagonal, no covariances. In Stata, the random intercept is requested by that blank spot right there. After you list a nesting variable, it automatically includes a random intercept variance for it. The independent residuals is the default, but I have written it here for transparency, that that's what we're asking for, because that is a choice. And in R, I am switching to LME because I want to be able to have R matrices of different kinds, as well as a random intercept variance in the G matrix at level 2. So the code looks a little bit different. The random part is right here, so that's adding a random intercept per person. And I do not have any correlation option, which means it's defaulting to no correlation in the R matrix with equal variances. That's what you get if you don't write anything. I'm asking it to then print the G matrix. So getVarCove is the function where there are different choices for what you'd like it to get. Random.effects is the G matrix. Type equals conditional is the R matrix, and type equals marginal is V, put back together again. So we can see what the model is saying about the data. I couldn't find an intraclass correlation function that goes with ALME, so I built my own. So I am taking the information that's in the V matrix and creating that. And then EM means to look at the mean differences, and ANOVA the same. So in R, there are two different ways that people specify models that have random slopes in them. LME is one of them. So LME is from the NLME package, which is the older of the two choices. The internet suggests that estimation is either slower or less efficient, maybe because of the way they did it, maybe because it's older. I'm not sure. I can't tell a difference in speed for the little examples that I use. What's good about LME is that it offers choices as to what kind of R matrix you can have. So you could add in, say, an autoregressive correlation of your residuals if you wanted to, or topolits if you could figure out how to do it. It's also good in that it has this getVarCove thing that allows you to easily see the pieces of your model and understand how they're being put back together again. What it's not good about is getting degrees of freedom right. So it's inconsistent across models and whether or not the denominator degrees of freedom actually are what they're supposed to be. It throws an error at me most of the time. So it's good at showing the variance model. It's not good at giving the right tests of the fixed effects, is what I have seen. So here's an alternative. Elmer is a different function from a different package, which is LME4. And I also there's an Elmer test package that goes with it that adds on stuff. And the good news about using Elmer is that it's supposed to be faster in terms of the way that it's programmed, and I think that is a consequence of the bad news. The bad news is that there is no choice for your R matrix. It is diagonal, the end. That makes everything a lot easier, but then you don't have that choice. So if you're planning to use Elmer, what you are essentially saying is, I'm going to take all the reasons the residuals are correlated, I'm going to put them in the random effects somehow, because there is no choice to just let them be correlated otherwise within this package. It also doesn't have built-in functions for showing G, V, or R, and I draw the line at having to do my own matrix operations in R. I added this to my birthday packet. That was the thing. So Jonathan's going to make me a package that fixes this, but he hasn't done it yet, because I sent him the list like 2 days before my birthday. So for now, unfortunately, the solution that I've landed on is to do it twice, because you have to estimate the same thing 2 different times to get all of the information and choices that you would have out of SAS, Stata, or even SPSS. I know. But it does get the degrees of freedom right. That is one thing that I've seen it do consistently. So if you're using Elmer, the code looks different. Rather than method equals REML, it's REML equals true. What do you think it would be if REML equals false? What would that leave you with?
ML?
Yeah, ML, the regular flavor maximum likelihood. That is also known, by the way, as FIML, for full information maximum likelihood. Both REML and regular ML are full information. This should really be called FREML, just like it's FIML, but for whatever reason it's not. But I've been trying to make FREML a thing for like 10 years at least. So FREML is what I call this. Instead of model, I think it's formula. So we have the outcome, squiggle, the fixed intercept, the saturated means for wave, and then the random part gets stuck in here in parentheses. So what is random right now is just the random intercept. And then the variable that's right here is random intercept per what. So that's your level 2 nesting identification variable, person ID. There is an add-on package I found that allows you to get an interclass correlation. So I added that. And then we can get the correct version of the f-test as well for saturated means. So let me make sure. Yeah, I think I said all the things I wanted to say about that. Any questions on code for this? We're good? Good enough? Cool. Moving right along. So here's what the model says. So you can think of this as model implied, model predicted. This is what it's supposed to look like according to the random intercept model. And so the variances on the diagonal here, all the same. Coincidence or consequence?
Consequence.
Consequence. This is a random intercept model. That's what you're saying. Covariances, all the same. Coincidence or consequence?
Consequence.
Consequence. Yeah, random intercepts is constant covariance or constant correlation. So we have the correlation that is implied right here that's constant. This is your interclass correlation, but it's conditional. So this describes the correlation of occasions from the same person after controlling for which occasion is which and allowing those saturated mean differences. Another way to say this is after controlling for mean differences over time, 65% of the remaining variation is between persons due to mean differences via the random intercept. So pretty high. Here are the 2 parameters that make up the model for the variance. So those are the ingredients by which we get the marginal V matrix put back together again. We have UN11, which in this case is your random intercept variance. That's because in the code, I have random intercept type equals UN right here, and that will always be what I have for the random line. The random effect variances get to be whatever they want. Unstructured is the only thing that would make sense. So that label refers to UN11 of the G matrix row 1, column 1 of the only thing that's in it. And wave, that's my residual variance because the residuals are structured by wave. Next up is the likelihood ratio test that tells us whether or not we need the random intercept. Survey says, yes, we do. So what this is, the 49 value here, that is the difference in -2 log likelihood relative to the same model that had only an E in the variance, just residual variance. So this is the model comparison of how much better the model got after adding the random intercept variance. Another way to think about it is that that is the significance test that goes with this intraclass correlation effect size. So the likelihood ratio test says, yes, there's person dependency due to mean differences. How much? Significant. How much? Significant. How much? 65%. Oh, okay. The rest of the output looks the same except for the standard errors are constant, whereas they varied last time with the changing variances. All right. So again, that's the alternative. If you can't fit everything, here's how you can cheat it a little bit to get just the focus on the mean side. Ready for the next one? All right, empty means. So this is starting from the worst possible model and moving up. So we're getting the 2 benchmarks essentially for our model comparisons. So here's the multi-level notation that goes with the empty model. At level 1, we have y, ti as the subscripts per time per person. So the first subscript is what's happening in level 1. The second subscript is what's happening in level 2. The first term in the level 1 equation is my beta 0 placeholder, and it has an I because each person is going to have their own version of beta 0 via the level 2 equation right here. So gamma 0, 0, what's that thing?
Fixed intercept.
Fixed intercept, which in this case is going to be the mean of the person means. And it's means and not intercepts at time 0 because time's not in the model yet. Likewise, what's U0? What's that thing? Random? Random. I heard it.
Intercept.
Intercept, yes. Remember, it's better to be wrong than vague. You've got this. I know you all do. I know it. And then E, level 1, that's my E that's left. So outcome equals nothing in SAS, that's my empty model. Random intercept in G, repeated wave with E only in the variance model. Outcome with nothing behind it is how I make an empty means model in Stata. Everything else looks the same as the other, random intercept only model. And here's both versions in R. So you can see them side by side. In your homeworks, by the way, I will tell you which package you should be using to get the right answers. I'm not going to make you guess. There is at least one model for which Elmer gives the wrong answers, but LME gave the right ones. I know that from last year. So LME then looks like this. I have nothing in the model for the means, just the 1. The random part is right here. Whereas in LME-R, the fixed and random parts all go into the formula as such, but it looks fairly similar. One new thing that we have here with LME-R is likelihood ratio tests. So this idea of whether or not we need the random intercept in the model, Stata gives that to you without asking, by the way. That shows up right under your solution for fixed effects as a test against linear regression. It shows up by default in SAS as well, so I'm adding it to R. And for whatever reason, the ANOVA function would not work with this package, but RUNOVA does. R in front of ANOVA. I don't know where that one comes from, if it's an LME4 thing or if it's Elmer test thing, but I do know that it works. And I also like this one because whenever I use R too much, I feel like I've been run over. Ba-doom, giving myself rim shots. But yeah, we're all going to be run over by the end of the semester. So you tell it what model you want.
I wanted to ask a quick question.
Yeah, hit me.
When we're talking about, we have the univariate repeating ANOVA and then the multivariate, like going back to that lecture,
Mhm.
does the empty means model correspond with one of those?
No, just the
Correctly?
variance side.
No, okay.
Yeah,
Okay.
ANOVAs are all saturated means. But-
Okay,
Yep.
that makes sense.
Yeah, we're on empty means because we're like I said, this is the worst model starting point that we're building from. Reduced term equals true means what it does is actually fit a series of models without each of the random effects that are in it. So it does actually more than one comparison, and you have to find the one that applies to you. But it's nice because then you don't have to do the math. Okay, other questions on this? Anything I can clarify?
Yes.
Yeah?
Can you repeat, please, the function of that piece of code, or what are we comparing here? Because likelihood ratio is for removing random intercept, but what we are changing here is fixed time and empty means.
So at this point, what it's comparing is a model for the variance that has a random effect versus one that does not, E only.
Okay.
So it has nothing to do with the fixed effects.
Oh, okay.
Yep.
Great.
And actually I think it will either yell at you or give you an error if you try to do model comparisons that differ in the fixed effects under REML, because that's not allowed.
Great. Yeah. Thank you.
Yep, yeah, so what it's doing behind the scenes is fitting a model that you didn't actually ask for, the E only version of this model, so that it has the -2 log likelihood from that to compare against.
Great.
That's what it's doing.
Yeah. Thank you.
Yep. Okay, others? All right. Nathan, I got you. Okay, moving on then. So then our first version of put back together again models, I think, or one of our first anyway. So here's my R matrix. So the diagonal of this represents what? What is 7 in my story here? It's a variance. I'll give you that. Which one? Level 1 or level 2?
Level 1.
Level 1, within or between?
Within.
Within, marginal or conditional?
Conditional.
Conditional, level 1 conditional within person. That's what we have here. This is the E variance. According to the model, it's 7. G matrix then. What kind of variance is that?
Random intercept variance.
Yeah, the other one. Random intercept variance at level 2. And is it between or within?
Between.
This is between. So if I take this 2 and just like stick it everywhere in this R matrix, then that gives me the marginal version of V. And yes, stick it everywhere is not a matrix operation, but for an intercept only it works. So this is the marginal predicted compound symmetry form that we have from our random intercept model. If I compute the correlation version of this, so random intercept variance, the 2.88 divided by the total, the 9.9, that's where the V-core comes from. And the intraclass correlation from this model is only 0.29. So the previous model that we looked at that wasn't empty, that had saturated means, the intraclass correlation then was 0.65. So this is what I mean by when you explain residual variance, which is what the saturated means had done, the random intercept variance has to go back up. So without it, it's a lot smaller, and it looks like there's less dependency. So there's not necessarily one version that's right and one version that's wrong. Just be clear about what you're reporting. So typically, I would see this version, because this is like the simplest possible model you would start from. So according to the empty means random intercept model, 29% of the variability in this outcome is because some people have higher means than others. The rest is within persons. And then here are the two parameters that make up those predicted matrices. Here's my likelihood ratio test comparing against E-only version. And then the fixed intercept is 12.8, which is my gamma 00 fixed effect. Okay. So now we add time to the story. This is the new model that we introduced on Tuesday. So in the multi-level model notation, at level 1, I still have my beta 0I placeholder for how each person is going to get their own intercept, and it's still made the same way. So the level 2 equation for beta 0 is the fixed intercept plus the random intercept. That hasn't changed. What has changed is the beta 1 component of level 1 right here, where each person is now going to get their own linear time slope. And according to this model, even though it has the capacity to allow each person to have their own slope, that's not what's in the model yet. It's just the fixed slope right here. So you can write out the model more simply by substituting out the placeholders and just putting in the fixed effects like this. So gamma 0, 0 plus u 0, that's my, each person gets their own intercept beta 0. Gamma 1, 0 is beta 1 at this point. So parallel change model. So how to fit it? SAS users, if there's any of you left at this point, there are two different variables in my code, time and wave. They are used for different things. Wave is on the class statement because it is in the repeated statement as the level 1 indicator for which occasion is which. It's an ID variable. Time goes on the model line, and it will eventually go on the random line as well, because that's the version that is being treated as a quantitative predictor. So time is quantitative. We are going to get a single slope for the change in the outcome per unit time. Wave is treated as a categorical ID variable. And they can literally be the exact copy of each other with different names. But you need two of them, or SAS will not like it. So wave goes 1 to 4 and time goes 0 to 3. But otherwise, they tell you the same thing. I'm also in SAS saving two pieces of output so that I can do math on them. One is for a likelihood ratio test in anticipation of adding the random slope. And the other is the model for the variance parameters in anticipation of doing effect size, how much of the variance went down. I'm also asking for the model predicted mean at each occasion. So these little estimate statements we talked about a couple weeks ago, but the idea is that the word that is in these refers to what the gamma fixed effect is going to be, and then the number that comes after it is the multiplier. So in this case, int means gamma 0, 0, and I need one of those for all of my predictions because all predictions start with an intercepted minimum. And then time is gamma 1, 0, and then what goes in parentheses for the time variable is the numbers right here, 0 to 3. And then last but not least, I wrote a little macro that does pseudo R-square calculations. So what it's going to do is take the variance components from the empty model and then create a table out of it within SAS, add the variance components from this model, and then compute how much they changed. So it's just me doing a little bit of math behind the scenes. In Stata, we now have C dot time as a fixed effect. So C dot means treated as a quantitative variable in Stata. Sometimes it's necessary and sometimes it's not to have the C dot, and I haven't cracked the code as to when it is, so I just stick it in always. It seems to be tied to the use of the fixed effects in linear combinations. That's when it seems like it cares. But these lincom statements do the same thing. Underscore CONS stands for the fixed intercept, and C dot time is going to be the fixed slope, and then these are the multipliers. The small, by the way, is to get T's instead of Z's. So it's asking for the use of the same denominator degrees of freedom that the model did. Otherwise, it defaults to Z's with no degrees of freedom. And those of you who are like, wait a minute, I use Stata all the time and I never write out these lincoms. I use margins. Yes, I know, but I wanted to show you what it would look like. So here is one line that does what the work of all four. So I can ask for predicted means as a for each level of this variable by putting them in parentheses like that. And what that means is start at 0, go in increments of 1, and go up to 3. So start by end on here, Gesundheit. And so that would give you all four means in one line. And I'm also storing the results of the analysis for a future likelihood ratio test to be. Okay. Questions on SAS or Stata for that? All right, R folks. So again, LME so that I can show you the structure of the variance model. LMER so that we can get the right test of the fixed effects. So I'm adding in time right here as a fixed effect. Note that time doesn't go in this part yet because that's where the random slopes go. So eventually you will have time in two different places because there's a fixed part and there's a random part. I am using, let's see here, this command right here adds -2 log likelihood AIC and BIC, which is not a default. And there's something about check REML that it didn't like, and so I turned it off and it worked. I'm not entirely sure what that's for, but I think it has to do with model comparisons and when it would not be valid using REML. The analog that I found to the estimate and LINCOM statements for use with LMER is this contest 1D function, which means a single degree of freedom linear combination. So it wants to know what model to use, what degrees of freedom to use, and then this thing right here. This is, let me highlight that, see if I can highlight both of them. No, not very easily. Okay. The order of these numbers matches the order of the fixed effects you requested in the model. So the 1, 0 means give me an intercept, but then don't use the slope for time. 1, 1 means give me an intercept and then multiply the slope for time by 1, because that's the occasion I want the prediction for. And so now you know why I stick 1 in here. It's not because I need to. It's to remind myself of the order of these things and to not forget the intercept. I also used a separate package that's called prediction that works like the Stata margins package, but it doesn't give me standard errors even though I asked it to. So I was like, all right, I give up. But it works just like the margins does in that you're allowed to specify a range of values over which to get predicted outcomes. And I'm sure there's other ways too. This way is cumbersome, but very, very flexible. Okay. Our folks, any questions on any pieces of the code here? All right. So, relative to the previous model, let's see what happened. So, to recap, we're adding a fixed linear time slope. Is time a time variable or a person variable? Time, yeah. So should it explain level 1 variance or level 2 variance?
1.
1. So should it explain R matrix variance or G matrix variance?
R matrix.
R, yeah. And here it is. This number on the diagonal of the within person level 1 conditional R matrix used to be 7, and it's down to 2. So part of the reason why the E's were going around the person means is because the line needed to be tilted, not flat. And the E's fit better once you have the right line in place. So in terms of proportion reduction, so I have the math in here in the text box. I also have an Excel sheet that goes with this example. All of my examples have Excel sheets for the calculations. I can compute how much of the level 1 residual variance went down. So it used to be 706 in the empty model. It is now currently 2.17. Divided by what it used to be gives me a 69% reduction. So in talking about R square, though, you have to resist the urge to end your sentence there. You cannot say the R square for the model is 0.69. Now, why is that wrong to say it that way? What do you think? If I just said the model explains 69% of the variance.
That'd be because it's only explaining variance in the R matrix, not the whole.
Yes. Which variance should be your question, right? Because that sentence is based in the world of linear regression where there's only one E and there's only one kind of variance you could possibly be talking about. But no. It's 69% of what was within persons. So now I got to think, how much within persons did we have originally? And if we go back to, let's see, it was 29% between, which means 71% within. Am my math correct on that? Yeah, I don't do math in front of people live. It's just a recipe for disaster. But 71% of all the variation in this data set was over time. Of that 71%, we got 69%. 69% of the 71%. So we'd have to multiply those two values together to get what the actual R-square would be put back together again overall. And I'm not doing that in my head. But 0.7 times 0.7, like 0.49, like half of it-ish. So we explained half of the total variance by explaining 69% of the 71% that was within persons. So the way that I would write this is I would say specifically a fixed linear time slope explained 69% of the level 1 residual within person variance specifically. So as long as you say which variance was explained, then you're good. And your reader would have already heard about the intraclass correlation in the previous paragraph. So they'd have a sense as to how much that is in an absolute way. Okay, does that make sense? Yeah, we're talking about proportions of proportions here. The random intercept variance used to be like 2.88, and now it's up to 4. So this is the increase in random intercept variance that is a consequence of having explained level 1 residual variance. So the conditional intraclass correlation from this model is much higher. It's 0.65. So conditional intraclass correlations quickly start to not be a thing, because what you have to think about is, like, of the variance that's left, 65% of it is because of person mean differences. Right, but that's not really fair, because the only thing we've tried to explain is time variance. We haven't tried to explain person variance yet. So you could have a conditional intraclass correlation that's high or low based on how good your model is for what should be left over at that point. So that's why I tend not to report those, because I think it's somewhat confusing and or unfair. So here's the two variance components. Here are my fixed effects. Oh, too far. Let's play interpret the numbers. Scroll back over, there we go. My intercept is 10. What's that mean? And Zoomers, I'm watching the chat if you'd like to play along.
To me, that would be the expected mean of individual means at time 0.
Yes, the expected mean at time 0. It's not the actual one. It's the one that's predicted by the end of the line. Right? So that's one thing to keep in mind. It's a prediction. Yep. So at time 0, people are predicted to be at 10.7 on this outcome. What happens to them according to this model as time goes on? Up or down? Up. By how much?
1.7.
1.7. What's the end of the sentence? Per time. There it is. Now, what is time? I don't know. I made up the data. Per week, per month, per day, whatever, per something. So it's a rate of change. Does this model say that time... Does this model say that the slope should eventually shut off, or does it go on forever? It goes on forever. This is a linear slope. So for only a couple of occasions, a linear slope is a reasonable thing, but in thinking about, like, theoretically what you're saying should keep happening, linear is probably not realistic in most settings. Eventually, people are going to stop changing, either because they hit the floor or ceiling of a measure, or because just growth eventually stops. Let's see. Let's note the difference in degrees of freedom here. Denominator degrees of freedom are going to start to look weird. They will have decimal values in them, and that is what happens. These are being estimated. So we'll talk about this later when we get to predictors, but Satterthwaite degrees of freedom tries to take into account what level the predictor is at and sort of how much variability it has at that level relative to how much variability is at that level in the outcome. So these two numbers are different, even though we're both thinking them as level 1 fixed effects, because the intercept is random. It's being treated as a level 2 variable, essentially, whereas time is being treated as a level 1 variable. So for small data sets, this matters. Satterthwaite, or the other one is Kenward-Roger, which is an extension of Satterthwaite that also messes with the standard errors. Those are what you want for small data. And if you're trying to fit the same model in SEM, it's got none of this. There's no denominator degrees of freedom. It's just z's and chi-squares. So this matters a lot more in small data than in large data, but that's one of the reasons why I have this example, because longitudinal data tends to be small. All right, there we go. So here's the estimate statements in terms of what the model predicts at each occasion. So these are the predicted means from a linear trend. Each of these numbers differs by 1.7. And here is the output from my pseudo R-square macro. So I have the covariance parameters from the empty model. So before we added fixed time, I have the same information from the current model. And in this macro, the last column tells you by what percent the variance changed. So here's my 69% of the residual variance went down because we added fixed time. The intercept variance went up by 42%. So this is why people say pseudo R-square, because you wouldn't ever see an R-square like in regular linear regression that went down, but it can. If you did adjusted R-square, you could, by the way. This is essentially the same as adjusted R-square. Okay. Oh, I forgot. One other thing I was going to say. Is the fixed slope for time significant? Yeah, it looks like it. How do I know? That number right here. So for fixed effects, you are allowed to stare at the t-test statistics and their p-values that show up on your output. You don't have to do likelihood ratio anything for fixed effects. And you can do that regardless of whether you're in ML or REML. That's always cool. It's for variance decisions that we need likelihood ratio tests. Okay. Random linear. That's what we have next, but we haven't talked about that yet. Okay, want to look at random linear very quickly? Very quickly. Okay, random linear slope in multi-level notation land. I'm on slide 22. What's the new thing on the slide that turns this into a random linear time model? It's one thing.
U1I.
There it is. This guy right here. That's it. And it's U1 because it goes with beta 1. It's U1I because each person gets their own. So U1 is my random time slope. It is how far off of the fixed time slope mine is. So it's phrased as a deviation. What I would call this model is just a random linear time model. So previously I had fixed linear time, comma, random intercept. This is random linear time. The reason that I don't have to say fixed linear time and random linear time in the title of the model is because it is implied. Whenever you have a random effect, you should always have the fixed effect that goes with it already, because the fixed effect is the middle. The random effect is varying around that middle point. So if I say random linear, that means I also have a fixed effect in the model. If you forget, and I once had an argument with a student from statistics about this who claimed that you could have a random slope without a fixed slope, I said, okay, you go try that. She came back, she's like, it didn't converge. I'm like, I know. If you forget it, you're saying this is exactly 0. And so that might be close in some contexts, but it probably isn't going to be true in most of them. So to prevent estimation problems and also to allow the fixed slope to move away from 0 however it needs to, we keep it. So if you have a random effect in your model, you got to have the fixed effect that goes with it. So these equations then are parallel in structure because they have to be. Fixed part plus random part. So now this model is saying people get to differ from each other in two ways. They differ in where they are on their intercepts at time 0, and they differ from each other in how they change. So there's two different reasons for and quantifications of person dependency. And what we get to see next week then is how that translates into a different predicted pattern of variance and covariance resulting from that random slope. But that's next week because it's 1:43. Fair, right? Yes, I keep an eye on the clock. It's right on my monitor here, so I don't just keep talking and ruin the rest of your day. Well, I'm going to ruin the rest of some of your days anyway, but, you know, not the ones that didn't sign up for the second class. All right, any questions before we call it a week? Yes, sir?
In this case, that fixed intercept, the interpretation is predicted mean outcome at time 0. The reason for that is because we are using time as factor? Or why? What is the predicted mean outcome? And not only the predicted outcome?
You don't have to say mean if you don't want to. I was just going for the idea that it's on average. Yeah, it's the expected outcome, but it's on average for everybody. So that's the part that everyone shares, then random tacks on how yours is different.
Right. Thank you.
Okay. Thanks, folks. Have a good weekend. Finish your homework on Monday, and we'll see you on Tuesday.